Okay, so another kind of problem you often get is where you have multiple long straight wires with currents flowing through them. Each of them is going to create a magnetic field, and we need to find what's the magnitude and the direction of the net magnetic field at a given point. So here we've got two wires. Current 1 is going in, current 2 is going out of the page, and we want to look at the top corner of that square, the top left-hand corner at point P, and figure out what's the net magnetic field. A magnetic field is a vector, so we're going to have to break those into components and add them like vectors. So remember, the magnetic field goes in circles around the current. So what you do is you take your right hand, you do it in a form of a fist, so your right fist rule, put your thumb in the direction of the current. So for wire 1, you put your thumb into the page, so then your fingers are going to go around in a circle that goes clockwise. And so if we were to extend the radius of that circle up to point P, you see that at point P, the magnetic field is going straight. That's right at the top of the circle. The magnetic field is going straight over towards the right. Okay, how about from wire 2? Well, wire 2, take your fist, put your thumb pointing out on top of I2, and you'll find that the magnetic field goes in a circle around. This time is going counterclockwise. And if we look at the point on the diagonal there, which is where point P is, you see that the magnetic field points down diagonally in the direction there shown by B2. So I've got two magnetic fields, B1 and B2. I need to find their magnitudes, and I need to find their components and add them together as vectors. And you might get a problem where it's got 3 or 4 or even more magnetic currents to do this with. All right, so let's start off with the magnetic field from wire 1. So B, remember, is mu 0 I over 2 pi r. We did this already in problem 2. So we know the size of our currents. It's given in the problem. And we know the distances, which is r. We know mu 0 is a constant. So let's just calculate the numbers. All right, so B1 is mu 0 I1 over 2 pi R1. Right, so mu 0 is 4 pi times 10 to the minus 7. I1 is 3.0 amps. Divide by 2 pi, and then divide by R1. So if we look at this picture here, let me get rid of my circles. R1, you can see, is just one side of the square. So R1 is just 5 centimeters. And remember, we always have to put that into the correct SI unit. So that's got to go to meters, 0.05 meters. So I put that in, I get 1.2 times 10 to the minus 5 Tesla. And that's straight in the plus x direction, that direction shown by the arrow there. All right, how about B2? B2 is going to be mu 0 I2 over 2 pi R2. All right, so mu 0, 4 pi times 10 to the minus 7. I2 is 4 amps. And now R2 you can see in the picture is the diagonal distance from wire 2 up to point P. So if I look at, let me draw that triangle again. So I've got 5 centimeters on each side, and I want to find R2 as the hypotenuse. R2 is going to be the square root of 5 squared plus 5 squared. Okay, so that's going to be, if I put that in my calculator, 7.07 centimeters, just using Pythagoras. So that's 0.0707 meters. So if I put that in the denominator, I get 1.13 times 10 to the minus 5 Tesla. So you can see these are quite small fields in terms of Tesla. Remember, 1 Tesla is a really, really big field. Okay, so now I need to get the components of these vectors and add them together. So we'll do like what we did in the first module when we were finding the net force and net field. Break it into components. So I'm going to make a little table, x and y components of B1 and B2. All right, so B1 is all in the x direction. So we're going to put the whole thing, 1.2 times 10 to the minus 5, in the x direction. and it's got nothing in the y direction. B2 now is going down at an angle. Let me pull that picture down a little bit so you can see it. Okay, so B2 is going diagonally there. So what angle is that? Well, diagonal of a square, that's at 45 degrees, right? So all these angles are 45 degrees. So if I draw my vector on here, let me do it. Looks like I moved my numbers a little bit. Not quite sure how I did that. Let me see what happened there. Okay, so let me erase this just because it looks a bit messy. So this is 1.2 times 10 to the minus 5 Tesla. And this is 1.13 times 10 to the minus 5 Tesla. All right, so let me draw my vector B. Let's see, I'll draw it on the left side here. So here's B2, and it's at an angle of 45 degrees. And I want to find the x component, which, let me draw it in green. So this is B2x, and B2y, I'll do that in blue. Okay, so if I look, I can see that the x component side, that side is adjacent to the angle, it's touching the angle, so that means we're going to use cosine. And B2y is opposite to the angle, so we're going to use sine. And another thing we can see is that B2x is going backwards, so it should be a negative. So I'm going to put a negative sign in front of it. B2y is going downwards, right? So we're in quadrant 3. So that means the x and y should both be negative. So I'm automatically going to put a minus sign in front of my numbers. All right, so let's find it. We know B2, the magnitude is 1.13 times 10 to the minus 5. So this is going to be minus 1.12 times 10 to the minus 5 cosine of 45. A little bit squeezed in there. And this one is going to be 1.12 times 10 to the minus 5 sine of 45. Okay, so now I need to get my total x component by adding down this column. All right, so I'm going to add those two numbers. So B total in the x direction is going to be 1.2 times 10 to the minus 5 in the plus x direction, minus 1.12 times 10 to the minus 5 cosine 45, which is in the minus x direction. I get 4.0 times 10 to the minus 6 Tesla, so it's net in the plus x direction. How about in the y direction? Y direction, now I'm going to add up those two numbers. So 0 minus 1.12 times 10 to the minus 5 sine of 45. So I get minus 7.99, so basically minus 8 times 10 to the minus 6 Tesla. Okay, so those are my components. We're asked to find the magnitude and the direction. So what we have to do is we need to draw the triangle. So let me again do it here on the left side. So I've got B total x is 4 times 10 to the minus 6. So I'm going to go 4 times 10 to the minus 6 in the plus x direction. Then the y direction, I'm going to go minus 8. Minus 7.99 times 10 to the minus 6. And so my net magnetic field is shown by that red arrow there. So B total is going to be the hypotenuse. So how do I get the magnitude? I just use Pythagoras. X squared plus y squared is equal to my total. So B total is equal to the square root of bx squared plus by squared. So that is the square root of 4 times 10 to the minus 6 squared plus negative 8 times 10 to the minus 6 squared. And so I get 8.94 times 10 to the minus 6 Tesla. What's the angle? Well, my angle, I'm going to find here, my angle, I always use a tangent. Tangent is opposite over adjacent. So tan theta is the opposite over the adjacent, which is minus 7.99 times 10 to the minus 6 over plus 4 times 10 to the minus 6. So those 10 to the minus 6 just cancel. So I can just put that in my calculator as minus 8 over 4, which is minus 2. So to get the angle, I take the inverse tan of minus 2. I get minus 63.43 degrees. And again, remember, whenever you report an angle, you need to report it with respect to the plus x direction. So the plus x direction and just goes straight over towards the right. So we would say the angle, the direction is 63.43 or 63.4 degrees below the plus x direction. Okay, so that's my final answer. If I'd had 3 wires, I would have just done another term, found another magnitude, broken it into components, and then added 3 terms to get the total x and the total y. Okay, my end video has disappeared. So let me see if I can get that back. There we go.